Hey everyone, this is Kai. In this video I'd like to show you how you generate FODMC input from scratch, that is only from a given molecular geometry. And in the second example I want to show you how you introduce lone FODs per atom if that is necessary in your system. Once more, we go into the examples folder, and as you can see, I got myself a molecule. I called it test_molecule. The very first step is to give it a visual analysis in order to analyze what kind of information we have to put into the FODMC. So we have a bunch of atoms. In white we have hydrogen, in gray we have carbon, in blue nitrogen, and in red we have oxygen. What I like to do is to show the atomic indices. As a reminder, ASE starts counting from 0 and not from 1, which we have to take into account when we write down the bond pattern in the system file. We can use the general knowledge of how many bonds an atom of a specific element usually forms. In order to analyze that, we can take, for example, the oxygen atoms in this molecule. Oxygen generally tends to form 2 bonds to its neighboring atoms. And as you can see, each of these oxygen atoms only has a carbon atom as a neighbor. And thus, we need a double bond between this carbon and this oxygen atom, and between this carbon and this oxygen atom. Accordingly, what we need to specify is a double bond between atom 6 and atom 7, and atom 10 and atom 11. Furthermore, we know that nitrogen, generally speaking, forms 3 bonds to its neighbors. And each of these nitrogen atoms in this molecule has 3 neighbors and will accordingly form 3 single bonds, which are already initialized automatically in the FODMC. With that, we don't have to worry about the nitrogen in this molecule. So with that, this part of the molecule is fine by specifying the double bonds here and here. So what we have to worry about is the bonding situation between these 2 carbon atoms. We can have a look at this carbon atom first. It has a double bond to the oxygen and a single bond to the nitrogen. And carbon tends to form 4 bonds with its neighbors. And with that, we need a single bond between these 2 atoms. Now looking at this atom, it'll form a single bond to the hydrogen and has a single bond to this carbon atom, and accordingly it needs a double bond to this other carbon atom. To summarize, we need a double bond between atom 2 and atom 4, we need a double bond between atom 6 and atom 7, and a double bond between atom 10 and atom 11. How do we do that? We take the molecular geometry, given here in angstroms, copy it to the top of our system file. Here I just introduced the fix1s option, which places the 1s FODs at the nuclear sites. And now we need to specify the bonds that we just analyzed. And we said between atom 2 and atom 4 we need a double bond. Between atom 6 and atom 7 we need a double bond. And between atom 10 and atom 11 we need a double bond. Everything else should be fine, such that we can run the code and analyze the output. First of all, we see that charge as well as spin are 0, which is a good sign, because this molecule is neither charged nor has a spin polarization. Of course, what you should do is to analyze the bonding information and the lone FODs for all the atoms. I'm not going to go into detail right now, but you should always do that. I'd like to go into detail about the visual analysis, where we can see that the fodMC generated a proper gas for this molecule. First of all, we have a double bond between this carbon and this oxygen, and we have a double bond between this carbon and this oxygen. So these double bonds are generated correctly. Furthermore, we have a double bond between these two carbon atoms, and the rest of the bonds are single bonds, which have been generated automatically. So the bonding situation is fine. And furthermore, we have two pairs of lone FODs on each of the oxygen atoms, which is exactly what we would expect. Furthermore, we have one pair of lone FODs on each of the nitrogen atoms, which in this case are oriented perpendicular to the molecular axis, which ensure the charge neutrality of the nitrogen atom. So with that, we can conclude that the generated gas from the fodMC is fine, and you could use this gas in a calculation. The other example I'd like to talk about today is the carbon monoxide molecule. Carbon monoxide is known to have a triple bond, and with that we can just specify that within the notation that we have used before. However, trying to generate a gas without specifying anything else will lead to certain problems. What we see is that we generated a gas which is spin polarized, and the carbon monoxide molecule is not spin polarized, so something is wrong here. Now if we visualize the generated gas, we see what's going on. The triple bond is generated correctly between the two atoms. However, we have a single unpaired lone FOD at the carbon side, and we have two up and one down lone FOD at the oxygen side, which leads to a spin polarization in this case. Now why is that? The automatic generation of the lone FODs is done as follows. We take, for example, the carbon atom, and we have a look how many bonds it forms to all its adjacent neighbors. In this case, we have 3 up and 3 down FODs in the bond. We know that the carbon atom itself has 4 valence electrons that it can contribute to a bonding situation, and we assume that half of the bonds, or half of the bond FODs, comes from the carbon atom in this case. Accordingly, as carbon has 4 valence electrons, it is left with a single one to make it charge neutral, which will then be placed in the lone FOD region. Similarly, oxygen has 6 valence electrons that it can contribute to bonds or lone FODs. Once more, we assume that half of the bond FODs come from the oxygen atom, and in order to stay charge neutral, it needs 3 more FODs, so we have 2 up and 1 down FOD, in the lone region. While this assumption usually works very well, in this particular case we need to specify the lone FODs explicitly to make the system spin unpolarized. How do we do that? It's done very similar to the specification of bond FODs. We use the atomic index in the very first position, in this case 1 for the carbon atom. And then in parentheses we have the number of up and down FODs, which we would like to be in the lone region. Similarly, for atomic index 2, which is the oxygen, we want to have 1 up and 1 down, so 1 lone pair in the lone region. And when we run the code, we see that the spin is gone. We are still charge neutral. And looking at this gas, we see that we now have a spin paired gas with a triple bond in between oxygen and carbon, while each of these atoms has 1 pair of up and down FODs in its lone region, which is exactly what you would want for the carbon monoxide molecule. That's it for this video. Thank you very much.